Alrighty, welcome. Today we'll be talking about smart pointer examples, a program that we will be converting into using smart pointers as opposed to raw pointers. This program is going to be something I'm using for an upcoming polymorphism video, but for now, to show you what this is a small little game where you move around this little green player and you can run into these red players and destroy them. And right now, it is currently using what we call raw pointers. Every time we create a new enemy or a new player, we're allocating memory for that player or enemy into the heap, and that's being stored in what we like to call a raw pointer. And raw pointers are fine, but at the same time, one thing you always have to remember when using a raw pointer is to destroy them. So going over this code real quick to show you what this program does. This is using the Pixel game engine, which I've been using for all my projects, so if you're unfamiliar with that, then you can look at previous videos to see how that works. I'm creating a renderable. Normally I create a decal. I don't know why this is here actually, but we only use one image. The renderable keeps it a decal and a sprite packed together, and so if we look at the game closely again, even though there were two colors of enemies, you'll see they're actually the same exact sprite. They don't look any different. So they're just colored differently. And so these players and enemies are all getting initialized here, passing along the image data. And then we get down to the update function, and it's actually pretty tidy. There's no specific code that's tied to players and enemies. This is an example for my upcoming polymorphism video, and so you'll see all the functions here are actually tied in both objects, object types, and we're just iterating through them and running their specific code. We can see that a little bit more up here. We have a generic object class. The object class stores properties about any type of object, has a constructor, and then it has some virtual functions. Virtual functions allow us to define functions that may have some code initially, but can be overwritten by child classes, which is what we do here. By default, we also draw every sprite centered and rotated based on their current rotation vector. Down here we have the player object, our first child class. It overrides the collision and update functions of the object class. And we also have the enemy class. We also have a blank overwritten update function. That doesn't even need to be there. But the player has specific update code for handling movement, so that we can move the player and not the enemy. And also it has collision code against the enemy to see if we are colliding with an enemy, kill that object, set its dead marker to true. So that's the overview of the project. Let's talk about the pointer aspect. Right now all objects are stored in a vector of raw object pointers, and I am currently running this code using raw pointers only. Again, if we looked here, we would see that it is indeed running this way. But I want to show you something a little interesting. Because we're using raw pointers and we've allocated memory into the heap, what do you think happens when we destroy an object by running into it? You'd think, well, it's gone, right? It might be gone on the screen, but is it gone from memory? Well, it's not, because in order to reclaim that memory, you have to specifically say you want to destroy the raw pointer and reobtain its memory. So here, I'm actually going to indent this code a little bit, and I'm going to add a breakpoint here. I'm going to have to recompile my code because I just changed it. But the reason why I'm doing this is by entering this erase if, which says delete enemies that are dead, we can actually see, oh, hold on. Let's add a condition here. So we're going to rearrange this a little bit here so I can get my point across. If the object's dead, we want to return true to tell the erase if standard function to destroy it. By the way, this is from C++20 standard, so it's fairly new. It's pretty fancy and very nice too. But if you return true here, that means you want the thing, the object, erased from the vector you specify. So I'm just going to profile this a little bit because I want to show you something interesting. As a reminder that raw pointers are kind of annoying to work with. When we go here and we hit this breakpoint, it means we are ready to destroy the object. We're saying return true, which is going to erase it. Now I'm going to do something interesting here. I found this process memory usage snapshot tool. And if we take a snapshot here, we can see how many heap allocations and the heap size of the program at this moment. Now when we get down here, I'm going to now disable this breakpoint here, although I could leave it there, it's only destroying one object, and hit continue. We're now at this breakpoint. I can take another snapshot of the heap, and you'll see the amount of allocations remains exactly the same. There's still 5,071, haven't changed at all. What this means for us, and this is a red flag, that if we've destroyed something and the heap allocations haven't gone down, it means we haven't properly destroyed our pointer, which is a problem. That memory still exists. So, of course, the easiest way to handle this is to type delete and then your pointer, and that will delete it from memory. If we did the same test again, let me move the breakpoint up here actually before we delete it. So we run into this, we're going to trigger this breakpoint. This line has not executed yet. I'm going to take a snapshot here, and then we'll take a snapshot when this exits. You'll see that we're down one allocation, which makes sense. We have removed one object from our heap, which means now we freed a little bit of memory, 0.11 kilobytes. So that's all well and dandy. But imagine you had a more complex program with many, many pointers, and you had to do something like manage a tile map, and you had to just make sure every tile was destroyed, and you had to make sure all the enemies inside that map was destroyed, and everything else was destroyed. Why can't we tie the deletion into the vector itself? So instead of just having to go through all this and call delete for every single vector, why don't we just make it so we can call a simple clear and delete every single thing at once? Well, that's what we can do with smart pointers, and that's the whole point of today's video. We're going to be converting this program into using smart pointers. I'm just returning this code to its original state here so we can work on it. So to start with, there are actually two types of smart pointers. There's unique pointers and shared pointers. I'll be going over a very specific use case of shared pointers at the end of this video because I did find a good use for them recently. But more often than not, you're probably just going to use unique pointers because smart pointers are all about ownership. Who's going to own these things? And right now, we want our objects vector to be the owner of all of these pointers. We don't want anything else to have control over that. So that's what we're going to be doing here. So to start off, we're not going to be holding raw object pointers anymore. We're going to be first changing this to hold unique pointers. You start that off with unique underscore pointer. You have to add in brackets here, as if you're using a template, and you have to type in the type of the pointer itself. So it would be object here. Unique pointer is a wrapper for a pointer. It manages itself so that when this goes out of scope, gets destroyed in C++ object terms, then it will also destroy the underlying pointer with it. And that's great for us because now if we call objects.clear or erase this from the vector, it goes with it. And this also means anytime there's a vector reallocation, it also properly handles the movement. It does all that automatically. So now we go down here. We have to allocate pointers. So firstly, we can't use the new syntax anymore. Typically, what I like to do is use standard make unique. In here, you have to provide what the class you are creating is. So in this case, we're making a unique player class. And it automatically figures out what the constructor arguments are. Unfortunately, it can't automatically deduce what initializer lists are, so you do have to specify what the types of those initializer lists are. In this case, I have an OLC float 2D vector, so I have to specify that in order for it to properly recognize that. I can then do the same thing for all of our enemies. I can go ahead and finish this up here. And so I've successfully added new unique pointers into our objects of vector. Next up, we have to refactor these. They're currently using raw pointers. When we want to iterate through a list with unique pointers in it, we're going to be getting a reference to those things and then grabbing a temporary raw pointer from those. We know the raw pointer is good while we're in this loop, because we don't handle erasing until the very end. If you were to try and erase something while you were in the middle of your loop, you could cause problems, because say you initialized like your pointer right here on this line, and then let's say right here, because we're inside, or excuse me, maybe like right here, let's say you decided you wanted to delete the object, right? You erased it from memory. You called like objects, erase, whatever. And so if you called objects erase and then that position, let's say you had a counter here, then suddenly this pointer up here is now invalid. And what happens once it's invalid? Well, now you have problems because that raw pointer is now pointing to possibly dead data. So that's probably the only thing you have to really concern yourself with when you're dealing with these. You generally don't want to ever delete pointers while you're in a loop. Save them for afterward. And this is I think this is very good, especially for game development, to mark things as ready to be killed, but don't kill them until you're out of the loop. So first things first, I like to use the auto syntax here. So we're going to get an auto reference to not necessarily an object, but a unique pointer for the object. So I'm going to call it pointer O. And once I get pointer O, I can actually grab the raw pointer by calling pointer O.get. And this pretty much replicates what I had before, just with one extra little step. And we can do the same for the other one. We can get an auto ref for pointer O2, object 2, and then that will be inside of the objects array as well. And what I'm doing here, what this code is for every object, we're going to check if it collides with every other object. And it's a very slow way to handle collisions, but it's a very fast way for me to show what we need to show today. So that's why we've got like two loops kind of nested in here. So then we get object 2 out of pointer O2.get. Get is basically your raw pointer wrapped inside of your unique pointer here. And that's what the autos are doing. They're grabbing the unique pointer from the vector. And if you've never tried to read this, it shows you what the auto deduction figured out. So this is an iterator value type, which translates into the unique pointer. Yeah, templates and auto deduction gets a little scary here, but I think you just have to use it for a while and you get more and more used to it. And then we're making sure both pointers are not equal to each other, because say it was the player checking the player, you don't want the player to check if it was colliding with itself. That doesn't even make sense. And then we have a distance check here. We got the distance formula, and then we're seeing if the distance is smaller than the two radii added together. Because circle collisions and radii are very easy to work with, this makes for a very simple collision formula. And the cool thing I did is I made it so both collision functions activate. So if you recall up here, the player had a collision check, and this is what's called, because of polymorphism, when this happens. And the enemy actually receives a collision check too. We just don't do anything with it because we're already handling it for the player. But both objects get a collision event, and then we do some updating and drawing, and finally erasing. Anyways, we've updated this to use smart pointers now, so what do we do about erasing? Well, we clearly don't get a raw pointer anymore out of this when we iterate through it. So again, I'm going to use an auto reference here to grab, again, not necessarily the object, we're grabbing the pointer to the object. So I like to change its name to say pointer O or something. And then we can grab the object from that pointer. Or, and here's another cool thing you can do when you have the unique pointer, is the operators for unique pointers, the arrow syntax and the dot syntax automatically, the arrow syntax already works for unique pointers or smart pointers in general. So that's very handy for us because now we can just type, if pointer is dead, we can return true, otherwise we can return false. So that again can be reduced down to just this. Then we have this left. So there we go. I'm going to leave it like this just to show we are indeed removing the pointer when we remove this from memory, from the heap. So first, let's give it a run. Just make sure it still works. I think there's going to be one little problem. But we'll see. It should tell us. If it doesn't, I'm a little surprised. Let's have a look. So it does look like the program works. I guess there's no problem really with it. What I was concerned about was whether or not these were gonna complain, because these originally accept object references. But if we look really carefully at the syntax I used here, I accepted a pointer and then I dereferenced it, so I got the original object back out of it. Again, a little bit confusing when you're trying to follow along, because first we grab a pointer from the smart pointer, a raw pointer from the smart pointer, then we have to dereference it, and that's what I'm passing as the collision handling. I mean, it starts to get a little confusing, but hopefully this will be made more clear, especially in the polymorphism video where we actually make this thing. So I'm not concerned about that right now. We're checking if this indeed deallocates the memory. So again, I'm going to run 2 breakpoints here, and we'll do a little bit of profiling on our app here. So once again, I have to add in the if statement, otherwise we have no way to stop here. Because if it returns false, we don't care to profile that, only when it returns true. And yeah, normally I'd use the other code because, well, it's shorter, but here we want to profile it, so we care about conditions where that object is finally dead. And I don't want this breakpoint yet. Okay, so let's go run into one of these. I'm going to go ahead and take a snapshot of our heap at this time. We've got 5,035 allocations, heap size is there. Now I'm going to add a breakpoint here, hit continue. And it stopped, take another snapshot. Boom, 1 allocation down, heap size down. Very good, we got the same result as before. And that's because we're using smart pointers now. We don't need that delete syntax anymore. We don't have to worry about what happens with that pointer in the background. Smart pointers will handle that all for us, and that's wonderful. I think this is absolutely beautiful, because now you don't have to worry about any memory leaks. You are just concerned with writing your program. And this is why I added that boundary check, because the key was quote-unquote held down. And yeah. So if I go ahead and remove all these, and just breakpoint somewhere, if we take another snapshot, it probably went up just because I had other stuff running. So like, one thing C++ likes to do is allocate things for later. Like it will clean itself up, but it's allocated other random things bits as it's run code through here and such. So, yeah, I was hoping to show it going down again, but I forgot to profile it right before I ran into those guys, so it is what it is. But I did want to show where we lost memory every time at that point. So that's good. And I mean, when you're allocating thousands and thousands of objects, you could easily lose track of 1 or 2 pointers. So there's one more thing I want to talk about, and it is the shared pointer. So a shared pointer works a little bit differently. Real quick here, let's say right now, this vector here is the sole owner of these pointers, right? We know that we can go to this vector to grab any object pointer we want. But let's say we had another place we want to store our pointer. So we got our list. Our list is going to be giant. And it is currently the owner of a pointer. And then the same pointer, like this is the pointer here with data. And then the same pointer is now wanting to be here too. And this is all abstract right now. But the idea being that if we want it to be in multiple places and we want it to exist, what happens when I delete it from the vector? Well, there's still a dangling pointer over here, right? And this is where shared pointers come into play. Because if it still exists here, then the smart pointer keeps it alive. It doesn't delete it. It's not until the connection where the second pointer gets deleted that finally the shared pointer itself gets deleted. And that's the concept of a shared pointer. Now, an actual practical application I found for this came up very recently for one of my games. I had this damage indicator. And if we had, say, an enemy unit here, and it would take damage, there would be this damage counter that popped up. And the damage counter would tell you how much health was lost, right? Boom, you took 14 damage. And that's all well and good, right? This damage counter was inside a list. And there might be more damage counters depending on what was going on in the game. Like there might be an enemy over here that got hurt a while ago, and he took 7 damage. And there might be, I don't know, a player over here, and maybe the player took like 4 damage. And each of these numbers were all stored in this vector in different locations in memory. And so I originally used a unique pointer for this because there was only one owner of these numbers, right? But then I came across a weird scenario. I wanted to develop a system where if I hit an enemy multiple times in a row, I wanted the same number to go up higher and higher. So let's say I had an attack that did 7, 7, 7, 7, 7 damage in a row. Like 5 times, like boom, 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 boom. But I didn't want this to show like a whole bunch of 7s overlaid like this, because then you couldn't read it, right? Instead, what I wanted to do was I wanted to say 7 on the first hit, then 14 on the second hit, and then 21 on the third hit. You can kind of see where I'm going with this. It's increasing combo-wise until all these numbers have displayed. And then maybe something else will hit it, if that was a player, and then another number would pop up. But that number wouldn't be counted towards the 35. So why does this matter for shared pointers? Well, in order to accomplish this, this needs to be controlled by, or this number has to be known by this enemy itself. Why? Because if I hit the enemy, I want to know if the enemy has a damage number attached to it already. So suddenly, you can see there's kind of a link here. The enemy has to know if it has a damage number tied to it, and the vector has to have a damage number stored inside of an array. Because the damage number has to be displayed on screen, and the damage number has to be tracked by this enemy. So basically, every single player, or every single entity, is going to have a I'm just gonna call this a damage number pointer. So every single enemy has a damage number pointer. So the player does, the enemies do, and every time a new damage number is created, it's assigned to 2 places, and this means it has to be a shared pointer. And so if this damage number has been, let's say the enemy has been hit, if the enemy has been hit within like 1/10 of a second, we can just increment the number that's already stored in pointer damage number. But by default, in this vector, with all these different damage numbers, it's keeping track of timers for these damage numbers. And when some amount of time has passed, this vector will say, well, this damage number is basically expired to me. I no longer care about it. So it's just going to sever its link at some point. And then there will only be one place where this number remains. And the only thing that cares about this number at this point is this object. And so we need to know if this number's timer is valid. And we can't know if that number's timer number's valid if there's no more link to it. So if it gets destroyed and the number's completely removed, you can't check if that number is valid anymore. You can only know if it exists if you are in control of that number. Sound a little complicated? Yeah. It was complicated when I first thought of how I was going to do this problem, because it is very much a brain challenge. But we can try to implement it to really show how this works. So first I'm going to make a vector, and this vector is going to contain not unique pointers, but shared pointers of damage numbers. We haven't created damage numbers yet, but we will. And I'm just going to store it under the name damage numbers. So let's create a struct for the damage number real quick. The damage number is a very simple object. It's got 2 parameters. It's got a position, which is where it's currently being displayed. It's actually got 3 parameters, excuse me. It's got a damage number indicating how much damage it's supposed to display. And it's also got a timer. The timer counts down towards 0, and when it hits 0, it's supposed to disappear. At least from the perspective of the vector. Now remember, even though it's gone from the vector, there will be something else holding a damage number as well. So we can head back up here. I need to actually move this struct because it needs to be known by both the player and the enemy. Well, objects in general. Every object will hold a damage number pointer. So they will each have a shared pointer as well. So this is a pointer damage number. Now that we have this set up, the next thing we're going to do is make it so we can get these damage numbers displaying on screen. I think that's the first important thing. We're not going to worry about incorporating this part of the shared pointer yet, but let's first get them just displaying on screen. And how am I going to do this? First, I'm going to add some health to every entity. Let's say everything starts at 100 health. We're also going to add a timer to indicate like an invulnerability timer. Yeah, I think that's a good name for it. Or we can shorten it a little bit. It's a little wordy, isn't it? Invuln timer. After taking damage, the invuln timer will trigger for some amount of time, and while the invuln timer is active, we won't be able to reduce health. So let's go down here now. So the internal update function is called for all objects and cannot be overwritten. So I made this internal update function to handle all global behaviors, stuff that other objects cannot override. So we know that every object will deal with this invuln timer, and every object will also deal with this health parameter. So if health is less than or equal to 0 at any point in time, then we'll set our dead flag to true. We know we're dead if we lose all of our health. The other thing we have to do is say if, and here I like to use these for timers. I just say invuln timer is equal to standard max, whichever is greater, 0, or the invuln timer minus how much time has passed in the game engine. This is a really clean and nice way to just say either keep it at 0 or subtract time from it. Same thing as saying this. So you can kind of see why I chose the standard max route. If invuln timer is greater than 0, subtract time from it, and then if it's less than 0, set to 0. That's what this does in a nutshell. And that's what I prefer, actually. So we have the invuln timer working, so if we ever set it, it will start counting down automatically. In addition, if their health is less than or equal to 0, they will be considered dead at this point. So carrying on from that, the next thing we have to do is make numbers display and handle health. So all I'm going to do for now is if we collide with an enemy, instead of considering them dead already, we're actually going to subtract some health from them. We're going to subtract, I'm going to say 10 health. So we'll go ahead and subtract 10 health from the enemies. And at that point in time, we'll also set their invuln timer to be 0.5. And because they have an invuln timer now, collision object.invuln timer has to be equal to 0. Otherwise, we can't hurt them. So something like that. Finally, we need to display the damage number itself. So we have to create a new damage number when we do this. Now, unfortunately, we don't have access to the damage numbers vector from here. So how are we going to handle creating a new number? We're going to have to either return the number, like how much damage was done, or we have to call some function that reaches out to here. I think it would be better to call a function that is defined there. So for the smart pointer example, I'm going to define a new function, and I'm also going to define damage numbers to be way up here. Just a little bit of project restructuring. And if we were making a multi-file project, this is probably the point in time where I would actually, we need to, I'm going to leave these down here. We're going to do something a little spicy. You can see we're running into this issue where we need to depend on something, but we need something else, but it's not defined yet, like a function. So I'm going to say create damage number, but I'm going to create it way up here. And I'm only going to define the definition here. We're going to define we're going to do the declaration here. We're going to do the definition of it a little later. And this is kind of a stepping stone into splitting your project up into multiple files. When you have to start doing this, this is usually the point where you know your project's getting a little too unwieldy. Anyways, moving on, we're creating a damage number. We get to choose where we want it to be located, so we'll be using a 2D floating point vector. So we indicate a position, and we indicate how much damage we've dealt for that damage number. So we have this function, but we haven't declared or defined it yet. We've only declared it. We're going to declare it down here after we've defined our damage numbers vector, and we're inside of our smart pointer example already, so we have access to damage numbers. So down here in create damage number, we're actually going to create the damage numbers themselves, or damage number. So we're pushing back a new shared pointer. So instead of make unique, we'll be using make shared. Very similar, right? And the constructor for this is 3 parameters. We can look up here if we need a little reference. Pause, damage, timer. We have 2 of the 3 parameters already straight from the function. The timer itself will be set to, let's say they stick around for 2 seconds before disappearing. And now that we have that, the final thing we have to do is render. So we can iterate through. Again, we'll use an auto ref loop for our pointer of objects inside, and I'll call this pointer damage number inside of our damage numbers list. And this time it'll give us a, if this is, capital N. And this time we get a standard shared pointer object out of this. So all we have to do here is use that information in order to draw a number on screen. So we're going to call the draw text decal is it draw text decal? I thought it was draw text decal. Draw string decal. There we go. I was close. The draw string decal function of the Pixel game engine accepts a position to draw it at, and we already know that, so we can reference pointer damage numbers pause. Again, remember, with these smart pointers, you have access to the arrow operator, and it'll directly reach for the raw pointer's values. So that's just a very nice shortcut. The text itself, we're going to convert a number to a string, and the number we are converting to is the damage number's damage. Finally, we can choose a color we want to draw it in. I'm going to choose a red color, because damage is usually indicated by red. I think that's all we need for now. Let's take a look. Looks like we missed something there. Member function already defined or declared here. Create damage number. Yes, it was defined up here, wasn't it? I suppose we can move some things around. And the compiler can figure it out for us. Alright, so at this point, I'm going to try running into one of these. Well, nothing happened. It's broken. No, but as you can see, I stood there for a while, and it did get deleted. So we can tell that it is deducting health from them. And if we were to breakpoint here, I'm sure we would see that. So here we took some health, or we're about to take some health. This is our player object, and the collision object is what we collided with. So if we were to take a look at the health parameter specifically, it's currently at 100. If we were to step over this, we would see it goes down to 90. So we are indeed taking away health. If I hit continue, we'll eventually hit this breakpoint again, if we run into it again. And we can do the same thing. You see the health goes down to 80. So our debugging clearly shows that that part is working, but the damage numbers are just not appearing. Right, so what went wrong? Well, I think we forgot something. Create damage number. Now, create damage number is not actually available for the player. It's only available for the smart pointer example class. So we have to share the smart pointer example object if we want to get access to that, at least through the collision function. So the easiest way to do that is to pass this along with it. And I tend to do this a lot. You can see this is being passed for its update and internal update. This just gives it access to some things, but then if we do this, we're going to have to redefine this to include it as well. So we'll go ahead and do that. So we'll have to redefine the functions that override it as well. And finally, I can now access the PGE, and the PGE has the create damage number function. I did this in the wrong place though. Now that we have access to the create damage number function, we can now create the damage number where we want it to be. So I want it to be created where the collision object is located. So I'll go ahead and do that. Collision object's position, and the damage number will be the amount of health we dealt, in this case 10. I'll go ahead and run this. We'll make sure we can see damage numbers. Excellent. They're overlapping right now. What we can do is we can make the damage numbers rise up over time. That way they don't stay there. And of course right now they don't fade away or disappear or anything. So we have to make that functionality real quick too. So, for the damage number, we'll do something similar to objects and we'll add an update function that reads stuff from the Pixel game engine. We don't need virtual because we're definitely not going to be making child classes out of this that are going to override the functionality. And inside the update function, we have to do a couple of things. First, we're going to subtract the timer by felapse time. When the timer is less than or equal to 0, we need to say it's time to delete this thing. So we'll need a new boolean. By default, we'll say dead is false. When timer is less than or equal to 0, this number is dead, which marks it for destruction. Again, we want to handle destruction outside of the main iterator loop. That way we can safely delete it without having any problems. Finally, we want the damage number to move up slowly over time so that we can see other damage numbers. So I'm just going to let the pause.y move up at a very steady, let's say 12 pixels a second. With that out of the way, I think that'll give us a much better damage number. Now we just have to finally handle the destruction of the number. So just like the erase if for objects, also we don't need all this anymore. I'm going to go ahead and shrink it back down to what it was before. A very nice simple check if it's dead. We can now do the same thing, but for damage numbers. We'll be using the erase if function again to handle that. Instead of pointer O, I'm just going to do a quick rename here using Control RR, pointer damage number. And since we're using the dead flag here, we should be good. We use the dead flag for it as well. So remove damage numbers that are dead. Let's check it out. We go. It doesn't look like it's moving, but that's because we forgot to call the update function, so nothing's updating yet. So on top of drawing, we're going to make sure to call pointer, damage number, update. Pass in felapse time and this engine. As a final note, I did call it pointer damage number with the capital D, so I'm going to do the same for that down there, just for the sake of consistency. Bothering me a little bit. Look again. There's our number. Now it's slowly rising, so we can see 10, 10, 10, 10, 10, 10. This is great. That works well. Additionally, since we're using shared pointers, they're actually getting deleted. So we can once again look at this and see the heap allocations being deleted, just to prove they're getting deleted. And I want to show a little extra fun property that shared pointers have. So, if they're dead, we're going to return true. Otherwise, we'll return false. And this makes it easier to debug this. So, we'll breakpoint here, so we can get a trigger when a damage number gets deleted. So here, that top damage number was finally ready to be deleted. I'm going to go ahead and perform a memory snapshot here, just like we did for profiling earlier, and then I'm going to hit continue, and we're down here. I'm going to take another snapshot, and we've lost one heap allocation, which means we successfully lost the shared pointer like before. I want to do one more, because I want to show you something else that's interesting when this happens. So the next damage number is ready to be deleted, but before it gets deleted, I want to actually look at the pointer here. A shared pointer has something a bit interesting. Where is it? Okay, it has this uses flag and weeks flag. We're more concerned with this uses flag. The uses tells us how many places this pointer is currently being used in. So I'm going to do something that we're going to be utilizing later anyways, and every time we create one of these pointers, not only am I going to create the damage number here, but I'm also going to send that damage number over to another object. So our create damage number function now has to return the pointer itself. So I'm going to actually expect it to give me a pointer back. And this is going to be a weak pointer. When we grab this make shared here, let me see. It's actually going to give us a shared pointer. So we're going to be pushing back this shared pointer into here. But at the same time, we also need this shared pointer somewhere else. So we're going to push it elsewhere. I think I'll save the weak pointer for next time. We'll just do it this way for now. So I'm going to return it as well. We're spreading the wealth. Share the wealth. And by doing this, we've suddenly created this kind of web where we're no longer just having... So inside of here, this pointer is currently a shared pointer, and we're passing it to here, and then we're also passing it here. So we're suddenly creating this web where we're now going to have pointers going all over the place. Now, originally we created the pointer here, but once we return from this function, this original pointer actually gets deleted. And then we just have two other copies of the pointer going elsewhere. So it's this creation and deletion of this shared pointer that I think is really important to grasp here as we continue to develop this. So now I'm back down here, and I was originally going to use a weak pointer, but I think weak pointers are only really useful in situations like down here, where you know it's going to exist for some amount of time. It doesn't really accomplish what we're trying to do here. But since create damage number returns a shared pointer, we now want to give that shared pointer over to our collision object as well. So here I'm going to grab that shared pointer, pointer damage number equals that, and then I want to pass that pointer over to our collision object. So remember we created earlier this pointer damage number variable. I'm finally going to assign it to the pointer damage number we provided here. And so now that shared pointer that started way up there is now going to be all the way down into here. And this is when things get interesting, because now we have more than one place where this pointer is located. More than one place where this pointer is owned. And this is very interesting. I'm placing a breakpoint here because I want to show you something that happens when we do this. So this will happen right when we run into a collision here. So the damage number got created by the create damage number function, and then returned to that shared pointer, which then got assigned to pointer damage number, or is about to. I'm going to go ahead and run this line. Okay, now that we've done that, we're going to take a look at pointer damage number here. It is a shared pointer, remember. Suddenly, there are 3 uses of this pointer. The shared pointer has been able to deduce exactly how many times it's been passed around. And this is the crazy part about shared pointer, is that it currently has 3 allocations. It has the one from here, which is currently stored in here. It has the new one stored right here. And it had the one that got inserted into that vector from earlier. So it is currently in 3 places at once. Now, once we leave this let's get out of here real quick. Once we leave this branch here and go back to here, in our call stack, we're going one back. There will only be two uses of this, because one gets deleted in the local scope. So let's just hit continue here, and we'll end up here. Now we want to take a look at, we go to this, and we go to damage numbers. We have one pointer in there, so we'll look at that pointer, and we look at that raw view, and there are two uses. So that temporary shared pointer got deleted in that scope. And so all we have left now is the one that's in the vector, and there's one more hanging out inside that enemy. And the enemy now knows, where's the enemy? The enemy now knows which damage number it was last assigned. So you can see where we're going with this. If the enemy has a damage number assigned, and it has only been a certain amount of time, we actually don't create a new damage number, but we add onto its previous number. So now we're going to do this. We're going to first check if the pointer damage number is not equal to null pointer. So originally it's going to be null pointer, or let's assign it just to be safe. You always want to assign defaults, that way you have no undefined behavior in your program. So let's be safe. Set it to null pointer at the beginning. Always try to set some defaults. So if it's not equal to null pointer, the first thing we want to do is see if the amount of time that has passed since we've created the number. So if the timer is greater than or equal to, so it lasts for 2 seconds, right? Let me make sure. When we created that damage number, we said it lasts for 2 seconds. So if the timer is still greater than or equal to 1.5, it's been less than half a second since, let's do 1. It's been less than 1 second since it's been hit. So instead of destroying the other number, or creating a new number, excuse me, we're actually going to take this number and modify it. So at this point, I'm going to take the number, and I'm going to modify it by saying damage plus equals 10 instead. And by doing this, we're kind of adding a combo to it. We can also reset the timer at this point, back to 2 seconds. And I know I'm hard coding some numbers in, but this is more for demonstration purposes. In a real program, the stuff like the 2 seconds and the 1 second, you would code those out so that you can control those constants later. But bear with me here. We're going to set the timer to 2. We also need to do something a little interesting. We don't want it to keep like floating up. I mean, we could make it keep floating up, but that'd be kind of weird. We want it to stop for a moment. So I think just to kind of visualize this, if we have a, we're not drawing. If we have an enemy here, and then we have our damage number here, and it's like rising up, right? Slowly but surely it's rising up. If it gets hit again, and we want to add to this combo number, I want to keep the number at its current spot, and then it just stops. It just chills there for a moment. And then it starts rising back up again. I think that'd be a more interesting effect. And we don't actually have to reset the timer. What we could do instead is pause the timer and run a different timer. So I think we'll do like a stop timer is what I'll call it. And the stop timer will be like 0.5 seconds. Something short, but something that says, okay, you're stopped. Add more numbers to you. And then when that amount of time passes, it continues rising. You know, I think it's better we do this 2 ways. Yeah, I don't want to make it too confusing, but I do want to make it look right. So if stop timer is greater than 0, or the timer left remaining is at least 1 second since it originally was created, Either of those conditions will cause the combo number to keep going up, or that damage number. So finally, we need to implement the stop timer real quick, because I've just been sitting here talking about it. So stop timer, let's start it at 0. I'm going to set default here for the normal timer too. If stop timer is greater than 0, we update the stop timer first. If the stop timer is less than or equal to 0, we update the normal timer. And we only update the position.y when the normal timer is going down. This behavior should give us what we want, where the number stops if the combo number goes up, but it continues accumulating. And this way, we can keep hitting it, it will keep stopping, it won't go up, it won't go anywhere. Let's take a look. I have a breakpoint here, let me remove that. That was from earlier. Oh boy, what have we done? Well, we kind of got something, because it's saying 20s instead of 10s, but then it's drawing a bunch of other numbers. So we kind of messed up, but I think it's because of this create damage number. We kept creating them anyways, so we're not really... Basically, if there's a null pointer, we create this. Now, if the amount of time has... If we had enough time that has passed as well, then we also don't care about this, and we would create a new pointer. So, there are two conditions. Either we don't have a damage number pointer yet, or we do have a damage number pointer, but it's kind of been a while since we hit it, so we just create a new damage number. In either of those conditions, we would create a new damage number here. So you can see this number going up, and if I stop and come back, it starts a new one. And now the enemy's dead. So this is great and all, but where does the shared pointer come into play? Well, if you think about it, we haven't really done anything to the shared pointer. If we reach a point where we need a new damage number, we just create a new damage number and let the other shared pointer disappear. And we're overwriting it too, see? Pointer damage number gets set to a new pointer. So what happens to the old pointer? Well, the old pointer actually gets destroyed at this moment. This is the beauty of it. Even though normally it would get destroyed from the vector because time ran out, it might still exist here just as a bonus. Let me show you that real quick. So here, we can have one of two scenarios. Either I hit the enemy, and then the number disappears, so it's not on screen anymore, but the number remains in memory. Let's pause anywhere. Let's pause here. So we're going to pause real quick and take a look at the objects array. And we're going to take a look at the first enemy. I believe the top one is the first enemy here. So we take a look, and it has a pointer to the damage number. That damage number that disappeared, it's still in memory. And you'll see it has one use, and this is the only place it's located. The other, the vector that originally had it doesn't have this damage number. In fact, it has no damage numbers right now. It has 0. So we can see it's still actually in memory, but it's not really memory leaking because we know eventually we're going to replace it. So at this point, I'm going to run into the enemy again. And at this point, we've gotten a pointer to a new damage number. So the old damage number had an address of 2039AD2E660. Not really important, right? And we can see it originally had a number of 10 damage. Well now, I'll pause again. You can see that has changed. This is a damage number with 20, because I made it go up to 20, and it's now got a new address, 2039AD2EF20. you can see that it's been replaced. Well, what happened to the old pointer? The old pointer just got deleted from memory. It was a heap allocation. Heap deallocation. So, how do we prove it's gone? Well, we can do a memory profile again. So let's go to the part where we would replace the number right here. And in this scenario, it would be here where the timer has been too long, so it would create a new number. So I'm going to breakpoint when this occurs, and we'll see what happens. So I'll go ahead and run to this enemy again, which would trigger the breakpoint here. And then we're going to first take a memory snapshot here. There's been 5,130 allocations. I'll now go ahead and run the first line here, which is going to create a new damage number. At this point, we haven't set the new damage number. It's still pointing to the old damage number, this 20. But we've got a pointer to a new one as well. So pointer damage numbers point to a new damage number with 10. So let's look at the heap allocations. We've gained one because we've created a brand new pointer in memory. I'm now going to run this line where we're going to take the damage number that was inside of pointer damage number here, which is still that old number, and replace it. So I'll run that line, and we'll do another check, and we've now lost a heap allocation because that old memory is gone. That number exists nowhere else in memory, so the smart pointer takes that shared pointer and removes it completely. And finally, we're just left with this one pointer here that's actually in two spots right now because it's now allocated to the vector and to this object. So if we look here at the pointers, keep clicking the wrong thing. We have three uses again. One of the uses is because we're in this control block. If we step out of this, we're out of this block, and now that gets deallocated. And we can track that by now looking at here, going to PGE object or damage numbers, looking at our one and only damage number, looking at the raw view, and we see there are now two uses because that first use right here is now deleted. I think this was a very creative use of shared pointers, and I think illustrates why shared pointers can be useful very well. They're very hard to use effectively, and there's not really that many use cases for them. But when you do have to pass shared pointers around, in a situation like this, where more than one thing needs ownership of the pointer, this is actually a great opportunity to use them. And so that's kind of why I wanted to create this video today, was to share one of the more unique uses of a shared pointer, and to really demonstrate what they're all about. Because most of the time we just see unique pointers and, oh, make sure this object has control of this pointer. I really hope this whole video today helps you understand a bit more about how we dynamically use unique pointers and shared pointers, smart pointers in general, compared to normal pointers, to really make our programming life easier and not have to worry about the nitty-gritty details of delete this pointer, don't delete this pointer. Because imagine if we had to deal with that for every single array and every single data structure in our program. It would be a nightmare to remember every allocation. Luckily, we can have C++ do it all for us with smart pointers. Hope you all enjoyed. Thanks for watching.